So the idea we pushed out there at the end of the last video is that thinking about impulse and momentum and the impulse momentum theorem is really just a reframing of what we already know of Newton's laws. And so let's start by coming back and thinking about Newton's first laws. And so Newton's first law, the way that we've talked about it up until now, says that objects at rest remain at rest and objects in motion continue to move in a straight line at a constant speed unless they're acted on by a net external force. And so all we're going to do, if we want to reframe this in terms of momentum, is to say, well, Newton's first law says that objects at rest remain at rest and objects in motion continue to move in a straight line at a constant speed unless their momentum is changed by a net external force. So these two conditions, remain at rest or moving in a straight line at a constant speed, again, at a constant speed in a straight line means that your speed doesn't change, your direction doesn't change, so your velocity doesn't change. If the mass of your object also doesn't change, then your momentum hasn't changed. A net external force fundamentally acts to change an object's momentum. So if you have an unbalanced external force acting on your object, that will change the object's momentum by either causing the object to speed up, slow down, or change direction. So that either the magnitude of the momentum changes or the direction of the momentum changes. So if your object's mass doesn't change and the velocity is constant, the momentum is constant. So your momentum doesn't change, which means your net impulse is zero, which means the net force acting on your object has to be zero. And of course, that means there must be no acceleration acting on your object. If the object's mass doesn't change and the velocity does change, well, then again, your momentum has to be changing, which means that there must be a non-zero net impulse acting on the object, which means there must be a non-zero net force acting on the object, which means your object is accelerating. The fact that it's accelerating is why its velocity is changing. So again, all these sort of connect together. The way that we've previously talked about Newton's laws really are just another way of talking about momentum. Well, same thing's true with Newton's second law. So again, we've talked about it up until now as the net force is equal to mass times acceleration. We know that the acceleration is just the derivative with respect to time of the velocity. And again, if I take that mass and it's constant, then I can put it back into the derivative. And so this means that I've got the derivative of mv, which is just the derivative of the momentum with respect to time. So here I've got the net force is equal to the time rate of change of the linear momentum. And so a change in either the magnitude or direction of an object's momentum requires an unbalanced net external force to act on the object over some amount of time. So again, if you're going to change an object's momentum, what you have to have is an unbalanced net force. If this side of the equation is zero, then that tells you that your momentum isn't changing. Now, of course, we can think of this, the net force equals dp dt, that's a derivative equation. We can turn it into an integral equation by, again, multiplying the dt over, integrating both sides, and what we end up with is this. And lo and behold, we've seen this before. That's the impulse momentum theorem. So part of what we're trying to highlight here is that the impulse momentum theorem is basically just the integral version of the derivative equation that we've been dealing with since early in the semester that we've called Newton's second law. And so why is it we want these two forms? Well, it ends up working out that these two forms have their own place where they're useful. When did we use Newton's second law? Well, we focused on times when the acceleration was constant, which means we knew what was going on with the forces. But of course, we may not have a very good sense of what's going on with the forces. So in situations where the forces acting on an object are complicated, it tends to be far easier, or at least it can be far easier, to instead of dealing with this mess in the integral, do this simple, or at least relatively simple calculation that says just calculate the change in the object's momentum. If you want to think about Newton's second law, effectively we're setting up sort of two different framings depending on the information you have. So one of them, of course, is going to use our F net equals ma. The other one is going to use the impulse momentum theorem, and so how on average that net force acts to change the momentum of an object by acting over some chunk of time. When do we use each of these expressions? Well, the one on the left we've seen we want to use when we have forces that are constant. It works out as a vector addition problem. And we're going to draw a free body diagram of the forces. Make a single diagram that shows those forces and how they act. And again, because they don't change, I can get away with making a single diagram. When do I want to use this expression on the right? Well, typically that's going to be when the forces are complicated, right? So in some sense, if this approach is difficult because what's going on with the forces is very complicated, which means the acceleration ends up being very complicated, then we're often going to jump over to this equation on the right and say, let's try dealing with this in terms of thinking about the impulse momentum theorem. So what are these forces doing on average is probably going to give us a good enough answer. Now, of course, this delta P means that we're not doing a vector addition problem, we're doing a vector subtraction problem to calculate the change in the object's momentum. And of course that means that we're going to draw momentum vector diagrams that are going to show the initial and final momentum. Two different ways to think about working a Newton's second law problem, and a lot of it just depends on how clean and constant are the forces that are acting on your system, or instead are they really complicated, or things that are going on are complicated enough that we would like to avoid dealing with that complicated math and just sort of think about how things are changing on average.